Hello class, welcome back. So what we want to talk about today is making molecules that are called diols. So diols are simply a molecule that has two alcohols in it. So you could have something that looks like this. So that's just an alcohol, but if I tacked on another one, we would have a diol. And we have seen how to make diols from previous chapters. So do you recall, let's say if we have a alkene and we treat it with osmium tetraoxide with NMO right there, what's going to happen? We are going to form a diol. But what type of diol do we have? We have a syn addition there. So that's our syn dihydroxylation forming a diol. Remember, if you take this same compound and you treat it with a different reagent, let's say, what's it called? The peroxy acids. So MCPBA, if we treat that with that, what would we get? In step 2, we add some acid there. We would have a very similar product, but what's the difference? They're added in an anti-fashion, right? So we've seen these, to form these diols, we've seen that in previous chapters. What are some other ways though? Well, we've just talked about reduction of ketones and aldehydes. So retrosynthetically, we could take this diol right here and be like, okay, how do we make this? Well, if we had this product right here, what if I started with this diketone? Well, that would, if I take this diketone, so if I look at it in the forward direction, if I take that diketone, 2, 3, 4, 5, 6, like this, and let's say I treat it with hydrogen gas with some palladium or platinum. Palladium, or we could use palladium like that. What's that going to do? That's going to reduce those ketones into alcohols. So this is another way to form diols. But remember that when you want to reduce a carbonyl, it requires a little bit more effort. So you could, in theory, well, let's backtrack a little bit. What would happen to this alkene if I treated it with this reagent right here? It would form the alkane, right? Or the cycloalkane. But if we added a double bond there, or let's add it over, let's put it right here. Ketone, alkene. And we treated it with these conditions right here. If you're very careful, because this takes so much more effort to reduce, you could selectively just reduce the alkene. Remember that from class? So that's just something to remember, that yes, you can reduce carbonyls with these conditions, but you have to force it. And the way you force it is elevated temperature. That's one way, or elevated pressure. So there's a diol right there. What are some other reagents that we could use to reduce these ketones into alcohols? We could do it in 2 steps. Lithium aluminum hydride, and then you would have step 2 where you would have just aqueous workup. All right. So that's one way to reduce a ketone into an alcohol, this lithium aluminum hydride. What's a reducing agent that's similar to lithium aluminum hydride? And that is sodium borohydride. sodium borohydride. And when you use sodium borohydride, you don't need to have a acidic workup. And that will also do the same transformation. So when we take a look at how to make diols, we have 5 reactions. We have the dihydroxylations. There's 2 versions where you can get the syn and the anti. And then these 3 reductions that I've just taught you. All right? Good, good. Is there anything else that we need to talk about with this? No. The next reaction that we want to talk about is something called the Grignard reaction. And a Grignard reaction is a way to make tertiary alcohols. So for example, generally, or the overall process is where you have a, let's see here, we have a ketone. Okay. If we treat that ketone with the Grignard reaction, which is simply something that looks like this. We have a R group, which is just alkyl, anything carbon. And then we have a magnesium and a halogen, which is bromine. If we do that in the first reaction, and then in a second reaction we have an aqueous or an acidic workup, what's going to happen is we're going to take this ketone and turn it into a tertiary alcohol. Do you see the overall transformation of what has happened here? These 2 carbons are right there still. This oxygen is still this oxygen, but now it is not a ketone, it is what? An alcohol. And then this R group right there is now attached. So we have basically formed, so if we clean this up, we have made a tertiary alcohol. So the Grignard reaction is another way of making alcohols. Now in order to do this, we need to understand how to make this Grignard reagent. Okay? We'll talk about how to make it and then take a look at why it's reactive. Why does it do this? Okay? So the first thing that we need to do is take a alkyl halide. So generally speaking, or a general reaction here, so X can be typically we see it with let's just go like this. You typically will see it with a bromine. An alkyl bromide there. And you're going to take that and you're going to react it with solid magnesium. And you're going to do that in ether. And the reason why you want to do it in ether is because when you make this Grignard reagent right here, it's very, very reactive with water. And so if there's any water present in this reaction, it's not going to work. And so when you take your alkyl halide, treat it with magnesium, now you see the S there, that's the solid magnesium, so it's just metal, solid metal, dissolved in ether. You will then just basically insert the magnesium in between this R and bromine, just like that. Now, you don't need to understand the mechanism about that, okay? So we could even have, what's interesting here, is we can even have a halogen attached to a sp2 hybridized carbon. And if you treat this reagent with these same conditions right here, you're going to get the generic formula. So you could represent it like this. This R group right here is the benzene ring. So I want to expand that out. So this R group, so it also looks like this. Like that. So you see how we go from here, we add our solid magnesium in ether to form our Grignard reagent right here. So we could change this R group to, let's say, a methyl. And then we would get our methyl over here. Pretty slick. So that's how you make the Grignard reagent. Class, I know I've stressed this and I've said it, but please make sure you realize it's in ether. Water is your enemy when you are doing a Grignard reaction. Now let's take a look at why is the Grignard reactive, okay? Because what's happening is that this species is electron rich. It can act as a base or a nucleophile. And so when we take a look at this carbon magnesium bond right there, it's, well, which between these two elements, magnesium and carbon, which one's more electronegative? You're going to find that carbon is more electronegative. So it's going to have more negative charge on the carbon. And because it's so more electronegative than magnesium, what we can say, and this is just to simplify the process, we could basically say that this Grignard reagent kind of more or less looks like this. Okay. That's not entirely true, okay? But we can kind of just visualize this reagent kind of looking like this. Now, why do I want it to kind of envision it like this? The reason is because when you take a look at the mechanism, when you have a ketone, can you see that in step 1 of the reaction, this Grignard reagent right here, which is also right here, can you see how that's going to come in here like this? And when that does that, what are we going to get? We're going to form an alkoxide, and then my methyl group's going to attach. And then in step 2, what's going to happen in step 2? That is the acidic workup. And so when you do the acidic workup, what's going to happen? Just a proton transfer. So let's draw what that product looks like over here. So if we go from here to over here, we have our acid. And so we're just going to protonate. So we have 3 lone pairs there. We'll protonate to get us our tertiary alcohol. Like that. Okay, so that's how you do it. But going back to this idea, why do I want to envision my Grignard reagent like this? Because it just helps with the mechanism. But can you still do it with this reagent here? So let me show you how to use it with that reagent. What if we have our ketone here? And I'm going to show my Grignard reagent here, but I'm going to represent it like this. Now I want you to compare and contrast this one down here to this one up here. Both are correct though. Both are 100% correct. If I don't like visualizing my Grignard reagent like this, but rather look at it like this, all you're going to do is take the electrons in that carbon-magnesium bond and you're going to use it to attack the electron poor carbonyl carbon. And go like that. And so that would form the same intermediate as above. We'll form our alkoxide. And then we would just do our acidic workup, just the same as above, to form our tertiary alcohol. So what's amazing and cool about this reaction is this is one way to form or create tertiary alcohols. Another reason as to why this reaction is so cool is the fact that you are forming a new carbon-carbon bond. Remember that whenever we can form carbon-carbon bonds, that is a very powerful reaction. Nature does it so well. People don't form carbon-carbon bonds very well, and so when we find these new reactions that can do it with relative ease, that's what we like to see. All right? Let's see here. Is there anything else? Yeah, let's talk about one other thing, because I mentioned that the Grignard reagent can also behave as a base. And so this explains as to why, if you have, let's just say, a general Grignard reaction, why is it so bad to have water present? Because if we have a water molecule, we know water can behave as an acid and a base. But in this particular scenario, the Grignard is going to be a stronger base than water. So water is going to behave as an acid. And so this carbon-magnesium bond is going to behave like a base and deprotonate water really rapidly and generate RH plus our hydroxide. Okay, so that's showing us, excuse me, this is just showing us that the Grignard can act as a electron-rich nucleophile, shown above, and a electron-rich base. Okay. Now let's take a look at a reaction with a Grignard reagent with a ester. So let's draw ourselves an ester here, like so. And what type of Grignard reagent do I want to use here? Let's do this one. Right. Now remember, pH stands for phenyl, which just means that it's a benzene ring. So that reagent would look like this. All right, that's what we're drawing there. And so we'll do a Grignard, and then step 2, we would have our acidic workup. Okay. What's going to happen now? Now I want you to compare and contrast this to, let's just say, a ketone. Okay. Now if I take these same conditions here, put them down here, what would our product be? It would be simply a alcohol, right? Like so. Boom. Perfect. But when we have an ester, look at what the difference between the two. We are now going to have a alcohol there. And let's see here. 1, 2, 3, 4. 1, 2, 3, 4. Got to make sure we have all our carbons here. And then we would add our phenyl there, like so. 1, 2, 3, 4. 1, 2, 3, 4. Okay, we got the right amount of carbons. 1, 2, 3, 4, 5. That's fine. 1, 2, 3, 4, 5. Okay. Do you see the difference between reacting to Grignard with a ketone or an aldehyde versus an ester? You can see that in an ester, you have added this alkyl group right there twice. But when you react it with a ketone, you only add it once. So when you're reacting it with an ester, you got to put in at least 2 equivalents, or you just say excess, because it's going to add twice. Now, why does it add twice? Well, that comes down to the mechanism. So if we take a look at our ester here, let's try to give ourselves enough space to draw this here. We see our Grignard reagent right there. We could draw it like so. What's the mechanism? Like so. All right. So that's going to give us alkoxide and then our phenyl like that. Now what's interesting is that the Grignard reagent is a basic molecule. So we're under basic conditions. So the lone pairs on that oxygen can collapse back down and then kick off that piece. And when that kicks that off, what do we have here? Let's not add any carbons here. Well, there we go. 1, 2, 3, 4, 1, 2, 3, 4. And then we would have our ethoxide floating around, right? Now just look at that. That is a ketone. And so since we have excess Grignard present, it's going to add the second time. Just like that. And that will generate our product here, our alkoxide, adding our other phenyl group. And now, what are we going to do? Step 2, which is the acidic workup. And I don't think I need to draw a proton transfer like there. Okay? So the reason why you can add the Grignard reagent twice to an ester is because you have this leaving group. And when that leaving group leaves, you generate a ketone or an aldehyde. And we've already seen previously that ketones and aldehydes react with Grignard reagents. Okay? So that's pretty cool. Let's see, what else? What do you think about, what if we had a carboxylic acid? What if we wanted to put a carbon on a carboxylic acid? So for example, what if we had something that looks like this, carboxylic acid, and we want to take our Grignard here, step 1, and then step 2, we would do our acidic workup. What would we expect to happen? Well, what do we want to happen? We want it to do the same thing that we've seen with ketones and esters. So we would want something that looks like this. And then this phenyl would come in like that. That's what we would want to have happen. That's what we're envisioning. But this reaction is not compatible. You cannot treat Grignard reagents with carboxylic acids. It doesn't work. And the reason why it doesn't work is because we have already shown previously that the Grignard reagent is basic. So instead of doing this nucleophilic attack that we hope would happen, like this, that's what we envision would happen to form that product, but it doesn't do that because what do we have here? We have a carboxylic acid, and that's very acidic. So your Grignard reagent is going to do that to form the carboxylate. And when you form the carboxylate, that's the product. Okay. So Grignard reactions or Grignard reagents are not compatible with carboxylic acids. Okay. Another thing that you need to be aware of is that when you're trying to make a Grignard reagent, you have to be careful that there aren't functional groups within your molecule that can react with the Grignard reagent. So I'll show you an example of that so you can understand what I mean. So let's just go back and try, how do we convert this alkyl halide into a Grignard reagent? Well, we would treat that with solid magnesium. What's our solvent? Better be ether. And then that would just generate, well, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Perfect, right? Okay. Now what if I changed it up a little bit? What if I put an alcohol? What if I had this molecule and I wanted to convert this into an alkyl halide? Well, we would attempt to do the same thing, and we would hope ever so much that we would get this compound like that, right? Okay, you would for a split second, because the problem with this starting material is the fact that the moment you form the Grignard reagent, it's going to react with itself. Because what do we have here? We have a very acidic proton right there. Because we've seen that the Grignards can behave as a base. So your Grignard reagents, if you want to form a Grignard reagent, you cannot have a functional group that's going to react with itself. So for example, alcohols on the alkyl halide are bad because the Grignard, once formed, will react with itself. What's another functional group that would be bad? That would be a carboxylic acid. You can't do this reaction, right? Because the Grignard would react with itself. Let's see, what's another bad functional group to have on there? A ketone, right? Because we've seen Grignards react with ketones. So if you have a ketone on your molecule when you're trying to form the Grignard reagent, that's a bad plan. So if we go back to our alcohol here, what if you have to have the alcohol there, but you need to make a Grignard? Now there's workarounds. And the workaround, which we won't discuss right now, is that we would protect this alcohol with a protecting group. And just like the word implies, we are protecting that alcohol from reacting with the Grignard. So after we form the Grignard with the alcohol protected, we then do the Grignard reaction. And after the Grignard reaction, we will unprotect, or deprotect the protected alcohol. And we'll talk more about that process later. Okay, so let's go back to this idea of making a Grignard reagent. What was the Grignard that I wanted to make? It was something like this. I wanted to go like this: magnesium solid, ether. No, not that. Okay. Recall how I said that won't work, right? And why won't it work? Because the Grignard reagent will then react with itself. So what we can do is attach something called a protecting group. I'll just go PG for protecting group. And if we have a protecting group on that alcohol, now it will be compatible with the Grignard. So this Grignard that we've just formed does not react with that species. So now we can take this Grignard right here and treat it with whatever reagent that we want. Let's say a ketone like that. So this would come in like so. So that's step one. Step two, we need to add an acidic workup there. And after we do that process, we would get this molecule here. Let's see here, let's see. Let's write it this way. So we have our ketone there, which is going to be like that, and our Grignard came in here. So this carbon is carbon 1, 2, 3, 4. So carbon 1 attacked the carbonyl. So that's the carbonyl that I'm starring. So that would have to be carbon 1, 2, 3, and 4. And then I received the numbering scheme here that on carbon 3 we have the OPG, like so. And then step 2 right here is going to do the acidic workup, which would then protonate that alkoxide to generate our alcohol. So we could take that molecule and just make it look a little bit prettier. So what do we have? We have 1, 2, 3, 4, 5, 6 carbons. So I could just go 2, 3, 4, 5, 6. And we could put our OPG right there. Let's see, and we have another methyl there. So this would be carbon 1, carbon 2, carbon 3, carbon 4. Right? Let's see, my numbering scheme is off here. Let's try that again. Let's just use this as our numbering scheme right there. 1, carbon 2, carbon 3, carbon 4. What's attached to carbon 3? The OPG. And then attached to carbon 1 is to that carbon. That is attached to an alcohol. Nope. Yeah. And then like so. There we go. Let's double check. How many carbons do we have total? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay. Now, we formed our tertiary alcohol. And now we can do another reaction. We'll go down here. And that's the deprotection. We're going to rip off this protecting group. And I'm not going to show you what that reagent is quite yet because you don't know what protecting group it is. Because depending on which protecting group you use determines what type of reagent you're going to use here to remove it. So I'll just say reagent. Reagent with a question mark. And you can remove that protecting group. So now after you remove it, you would just have your normal alcohol. And there's your product now. Okay? So that's what protecting groups do. They make it not reactive. So let's take a look at a very common protecting group that protects alcohols. Since this whole chapter is about making alcohols, it makes sense that, hey, let's talk about a common protecting group that protects alcohols, okay? And a very common protecting group for alcohols is abbreviated. Let's find some space here. TMS, right there. Let's see, and that stands for trimethyl. Okay. Silyl group. Let's make sure I spell this right. All right. The trimethylsilyl group. So when we look at this reaction here, how would we demonstrate that this alcohol group is protected? We would just go O, TMS. All the way through. Just like that. Right, just like that. Now, what does trimethylsilyl group look like? Well, this silyl right there, remember that is, when we look at the periodic table here, we have carbon, nitrogen, oxygen, fluorine, right? What's below carbon? Our silicon. And so that's the sil right there. So when we take a look at the structure of this protecting group, what does it look like? We can represent it with the TMS there, but it's simply just a Si. There's our silicon atom. And what's attached to it? Trimethyl. So a CH3, CH3, and a CH3 like that. Now, why is that a good protecting group when you're trying to form a Grignard reagent? Well, because now, let's look at before and after. Why wouldn't this form the Grignard reagent? Well, because we have that acidic proton there. That makes it not work. But now, when you have the silyl group attached, there's no acidic protons. So there's nothing on this group here that the Grignard would react with. Okay? So that's what it looks like. Other ways that you could see it, instead of drawing out the methyls, don't let this confuse you, they would just do the Me. Me stands for methyl, right? That's another way of taking a look at it. So how do we put on the TMS group? All right. Now, it's really straightforward. Let's just look at a small alcohol. And the reason why I'm doing a smaller alcohol is just so it's easier to draw. Okay. So if we have an alcohol there, we would treat it with our reagent, TMS chloride. Okay. So that would look like this. We would have our silicon atom right there. And so those would be MEs, right? And then we would have our chlorine right there. So that molecule this molecule right here can be abbreviated like that. Okay? And so you're going to treat the alcohol with this, and also you're going to have a little bit of base. And triethylamine is a good base to use right there. And then those are the reaction conditions to get us to our protected molecule there. But the way that this proceeds is quite interesting. And the way we describe the mechanism is that we say it's SN2-like. It's SN2-like, or we could just say it's SN2-Si for silicon. Because what's happening here is that this is proceeding via an SN2 mechanism. So this is going to come in and kick off the chlorine like that. You will then have your alcohol. Draw that like that. That's going to be positively charged. And then our base, our triethylamine, would come in and do the deprotonation to form our product. Like this. Now, why should you be freaking out about this mechanism? Because what if I tried to do that with carbon? What if I try to do that? Most, if not all of you, would be like, that can't happen. Why? Because that is a tertiary alkyl halide. This also kind of looks like a tertiary alkyl halide, doesn't it? But what's the difference? We can clearly see the difference. This is a carbon atom, and this is a silicon atom. So when it's a silicon atom, even though it's tertiary, it still can undergo an SN2-like mechanism. If it's a carbon, it can't. It's too sterically hindered. And if we draw a space-filling model, which I can't really do very well. So I'm going to attempt it and see if it works. And if it doesn't, then we will talk about it in class so I can show you a picture, okay? So what I'm going to attempt to do next is why is it okay to do a SN2 on this guy but not this guy? Now, if you have to grab your model kit so you can see this a little bit better, I highly recommend it. But what we have here is we have our tertiary alkyl halide. And what I want you to do is when you build your model of this, I just want you to grab just the chlorine atom. Just grab the chlorine atom, and then you're just going to hold that chlorine atom and point it out, and then you're just going to see the 3 methyl groups all just pointing out at you. Or if you want to hold it like this backwards, you'll see that you have the 3 methyl groups all pointing out at you. And the reason why I want to show it that way is because what's going to happen? What we envision is that our nucleophile here, which would be just some kind of alcohol, it would come in backside attack. So you can see that this chlorine is inside the glass, and so if it's inside the glass, the alcohol is going to have to come in from backside attack and hit it. Okay. So why can't the alcohol come in backside attack? It's because if we take a look at these methyl groups right here and represent them as molecules, okay, do you see how they take up a lot of space? And so this alcohol is going to have a really hard time to get to the carbon because these methyl groups are in the way. So that same process here applies to the silicon. We have a space-filling model here, right? And you would envision that the alcohol would also have the same problem. It couldn't attack backside because all these the methyl groups are in the way. But what's different? This one's carbon, this one's silicon. They're different sizes. So if I represent these 3 circles for the carbon species, it's kind of like this. We have our space-filling model here, okay? And right here, let's choose a different color. That space right in there, in pink, that is the carbon, okay? So do you see just the surface area of that little pink blob right there? So that's very, very small and impossible for the alcohol to come in here and attack it because it can't get to the carbon. But look at the space-filling model with the silicon. What's different about it? I'm trying to draw these methyls the same size here. All right. And we'll draw this in pink here. Look at that space right there. That pink circle right there, that space, let's not draw it as a circle. That pink space right there is the silicon atom. And so because you see that there's more surface area, so now when the alcohol comes in to attack, it can, because there's enough silicon atom there to attack. So why is this so small and this so large? Well, because carbon atoms are higher up on the periodic table than silicon. Silicon is just a much larger atom. All right. And because silicon is such a larger atom than carbon, these methyl groups don't shield or protect the silicon atom as well as in this situation. All right? So when that alcohol comes in, it can get to that silicon atom. backside attack. It still has to be backside attack though, because it can't attack front side with the leaving group, right? Okay. So the last little thing that we need to talk about now is after you've put your protecting group on and you've done your reaction of interest, and now you want to take off the protecting group. How do you do that? So let's just take a look at an alcohol. We'll do our TMS chloride with triethylamine. That would give us this. Okay. And now, just for kicks and giggles so we can show you how to do it, let's take off the TMS. I'm not going to do additional reactions. I'm just going to say, okay, put it on, take it off, so you can see what that looks like. So how do we take it off? With TMS, these conditions are specific for TMS. You could treat it just with some acid, okay? And then that would give us our alcohol. Just pops it off. Another way that you could do it, or you could treat it with fluoride ions. And the way that you get these ions is using TBAF right there. So TBAF is tetrabutyl. So tetrabutyl ammonium. And what do you think the F stands for? Fluoride. There we go. Oh, that doesn't look right. Fluoride. Okay. So those are the conditions that we need to remember. Trimethylsilyl chloride with some base puts it on, and TBAF takes it off. Okay. And I'm not too worried that you understand the mechanism of how it takes off the TMS group, and not too concerned about that. Just remember what it does. Okay. Okay, that's a good place to stop. So, as always, if you have any questions or concerns, please let me know.